Okay. So today we're going to go through project 3, which includes practicals 3.1, 3.2, and 3.3 in your lab manual. The pre-lab and results sheets for this Prac are due on the 21st of September. I'll just ask if you can put in the chat real quickly that you guys can all see my slideshow presentation. Screen sharing is working okay. I'd hate to go through half of it and realize you can't see it. Okay, thanks, Zach. Cool, thank you guys. And as usual, I'll go through things pretty slowly and at a pretty basic level. And I'm sorry if it's too simple for some of you, but on the other hand, if you do have any questions about anything at any time, please interrupt me. Feel free to turn your microphone on or type in the chat. I'm more than happy to stop along the way. You don't have to wait till the end. Okay, so the pre-lab and results sheets are due on the 21st of September, so make sure you get them in. I'm fairly sure it's a midnight due date, but obviously don't leave it too late. Attempt it early, so if you have any questions, you can ask us. A good time to ask is in these practical sessions or in the tutorial sessions, the last half hour that myself or Matt take care of. Or certainly you can email us. Just keep in mind, as per the recent announcement, please don't email and just ask us for the answer to a question. At least show that you've attempted the question or attempted an understanding of the question. And if you don't understand where you're going wrong or you're not sure of something, definitely email us and we'll do our best to help you. But we can't, for items that haven't been submitted and marked yet, we can't just give answers, obviously. So keep that in mind when emailing us. Will be a lot more helpful if you pose the question in a way that shows that you've done some work as well, not just kind of expecting the answer on a silver platter, because all we'll do then is send you to various resources. Okay, so we'll get started on this this Prac or this project. So it's to do with metal acetylacetonates, so complexes of metals and the ligand acetylacetone. Like I said, it incorporates 3 different experiments in your lab manual, which we'll go through today. And basically, it's pretty similar to what you'd be doing if we were allowed on campus. Unfortunately, we can't have campus access at the moment, but if we were on campus, we'd prepare the complex in 3.1 and purify it. And then 2 weeks later, we'd come in and we'd do the IR, or you guys would run the IR. It's a pretty simple process, only takes about a minute to collect the spectrum. And it's a pretty simple loading procedure and that kind of thing. The NMR, if we were on campus, the NMRs, we'd provide you a printout because, well, for a proton NMR, it takes about 10 minutes. For a carbon NMR, 13C NMR, it can take overnight, like 12 hours. So obviously we couldn't do that for everybody in the class. Also, depending on where you are, Campbelltown, we have NMR facilities. Parramatta, we don't anymore. And there's a lot of kind of safety and induction to run the NMRs. So even if we were on campus, you would just get a printout of the NMR. So very similar to how we've done it this semester online. Unfortunately, we can't go in and run IRs. So again, you're just getting a printout of the IR spectrum to interpret. And the worst of all is that we can't go in and actually do the experiment and make the compound, unfortunately. So the best we could do is make a video and upload it to views. So that's what you'll be working off to complete this experiment. The demonstration video on views, the introduction video that I've done for theory and background, which a lot of it will cover today as well. The printout of the spectrum, and this session as well, which will allow you to ask any questions and hopefully give you a more of an understanding and a better idea how to complete the results sheet. So with all of that combined, hopefully it's almost simulating a Prac experience for you guys, and you'll be able to complete the results sheets, not only getting good marks, but also with an understanding, like a decent understanding of what we're actually doing in this Prac. Okay, so we'll start with preparation of the compound. So we've got here triacetylacetonato aluminium 3. So let me see if I can annotate. I'm not real good at Zoom, but let me do my best. So we've gone through the naming of compounds in various tutorials, and you've done it in the quizzes as well. And we can see from this, the name of this experiment, we can quickly identify what the compound's going to look like. So if we draw some square brackets around the complex here, we see that there's no counter ion, there's no chloride or nitrate or anything. So it's a neutrally charged complex. We can see that straight away. We can also have a look then at the ligand. We can see that there's going to be 3 of the acetylacetone ligands, and we can also see that they're going to be negatively charged because we've got an O appended to the ligand name. So we see it's going to be a negatively charged ligand, and we've got 3 of them. So the ligand charge overall is going to be -3, and we see that the aluminium has got a +3 charge, oxidation number of 3. So even if we didn't kind of have these structures available to us, let me go back. Just based on the name, we could pretty easily work out what we're looking at here. And there we have the structure on the left and a little model on the right. So you can see that it's a 3-to-1 complex. So you've got 3 of the ligands coordinating to the 1 metal center. They're bidentate ligands, right? And it's an octahedral geometry with a coordination number of 6. So you can see a lot just from the name and looking at the structure. Okay, we'll have a closer look at the ACAC ligand here. I'll be calling it ACAC from now on. It's a lot easier to get my mouth around than acetylacetone. So ACAC's quite an accepted shortened version of the name of the ligand. And you can see down the bottom here that it exists in equilibrium between a diketo and an enol form. So we'll have a close look at that in just a little bit. Some information about the ligand, some pertinent information here. Probably an important thing to look at is the melting and boiling points here. So looking at that, can anyone tell me what state the ligand would be in at room temperature, assuming that we're doing this experiment at room temperature? We're measuring out reagents at room temperature.
Would it be liquid?
Yes, it would be. Yep, correct. Because room temperature is, around about between 20 and 25 degrees Celsius. So it's already going to be melted. It's not going to be solid, and it's not going to be evaporated. It's not going to be boiling off into a gas. So we're going to be looking at a liquid. So that's one important thing to note from this information. And because of that, we've given you the density here, right? So you'll need to use the density to convert it from a volume to a mass. And then you'll need to use the molar mass to work out how many moles we've got, or how many moles you're using of the ACAC ligand. The other thing to note here, we've given you a solubility value, 16 grams per 100 mils. That's pretty soluble, relatively soluble. So that's an important thing to watch out for when you're looking at the demonstration videos of the Prac and making your observations about what's going on. Keep in mind the solubility that we've given you there. Okay. So the structure of the ACAC ligand. So like I said, it exists in equilibrium between a keto and enol form. So here we have it in the diketo form and in equilibrium with the enol form. It's called diketo. You probably know this from other chemistry units that you've done. This group here carbon double bonded to an oxygen is a ketone, and obviously we've got two of them. So it's a diketo. And like I said, it exists in equilibrium with the enol form. And how that happens is either of these oxygens, it doesn't matter which one, but both of them are very electronegative, right? So they can come pick up a proton, and when it does that, this double bond flips down there, and that's what you can see in the enol form here. Importantly, this system in protic solvents, so aqueous solution or alcoholic solvents, ethanol and methanol, also exists in equilibrium with a deprotonated form. So you can see the protons hopped off the alcohol group there, OH. And because of that, we can say that acetyl-acetone is a weak acid because it, as we know, acids are proton donors. And so ACAC doesn't mind losing a proton. It doesn't mind donating a proton. So it's a weak acid. And that is because the negative charge here, formal negative charge left by the proton that leaves, is actually carried in this conjugated system between the two carbonyl groups. And you can see that represented here in the complex. You've got this conjugation happening in the ligands. So because that negative charge can be carried in that conjugated system, the conjugate base that we see here is somewhat stable. So that means it doesn't mind losing its proton. So we can say that acetyl-acetone is a weak acid. And you see here the empirical formula there where we've got the protonated and deprotonated forms in equilibrium with each other. So like I said, that equilibrium happens in protic solvents because the proton can exchange with the solvent. And what you will have noticed if you've watched the Prac video already, or what you will notice, is that we can actually drive that equilibrium to the right. We can drive that reaction to the right by putting our ACAC ligand in basic conditions. And this actually grabs the proton. The basic conditions, obviously base is a proton acceptor. So to grab the proton and it will leave us with our deprotonated ACAC with the negative charge. So that's why in the deprotonated form, you'll see it's got this formal negative charge. And that's why our ACAC ligand overall has a -1 charge. It's been deprotonated. One thing I've noticed, I'll just say one thing I've noticed with these Zoom sessions, which is different to Blackboard. I wish we were hosting these on Blackboard. A lot of the animations in these PowerPoint slides don't work. So some of them you're just going to have to imagine, but I'll try and talk you through it anyway. So that's in basic conditions. We end up with the deprotonated ACAC- form. Part of your prac here is interpreting NMR. So we'll just stop here and have a look at the ACAC ligand itself in regards to NMR, specifically proton NMR. And can anyone tell me how many proton signals we'd be expecting for this ACAC ligand? Three is one guess. Any further guesses? Everyone's thinking the same. Okay. Yeah, Zachariah, you're on the right track there. It's considered symmetrical. Like I said, this negative charge is actually delocalized through this conjugated system. So there's just as much chance for the negative charge to be here as it is to be here. So we consider it symmetrical. So yeah, with that in mind, we can draw a line of symmetry, a very wobbly line of symmetry down the middle here. And we can treat this as our independent system that we're going to be looking at NMR. So when you do that, you can see that so all of these protons, as we've discussed in tutorials and such, all of these protons are in the same chemical environment. Does everyone understand why those protons are equivalent? Why they show up as one signal? Or does anyone not understand? And we can quickly talk about it now. Just let me know if that's unclear, but either way, we'll keep going. So those protons are all equivalent, so they'll come up as one signal. And this proton is obviously in a very different chemical environment, so that come up as a second signal. Given that we have two signals, one for this CH3 and one for this conjugated CH, what would be one very obvious difference that you would see between those signals? Like, how would you tell them apart on an NMR spectrum? Any ideas? Yep, both correct, Rebecca and Karen. I hope I've said that correctly. Chemical shift and integration. So they're definitely going to have a different chemical shift, but even without looking at that and deciding which one's going to be more de-shielded, you can very quickly and unequivocally decide that this signal is going to have an integration value 3 times this signal here. That's supposed to be a 1. It's a very wobbly 1, right? Because you've got 1 proton represented for this chemical environment and 3 protons represented in this chemical environment. So even just looking at the spectra and not kind of having to understand the shielding, de-shielding, and shift, you can have a look at, and there's a very wobbly spectrum. You can have a look at the integration. If the integration, say, 35 to 11.5 or something, which is roughly 3 to 1, you could assign, if we call this protons A, we could assign this peak to A and this one to B. So yeah, very quickly, without even thinking about de-shielding, you could pretty easily decide which signal belongs to which set of protons. And also, yeah, Zach, you're on the right track that you have to think about the axis of symmetry as well and how many equivalent protons there are. So hopefully that helps you guys with the results sheet a little bit. Cameron, wouldn't B have a higher chemical shift because it's between 2 oxygens rather than 1? Yeah, so potentially yes, potentially yes. Not kind of categorically because it's between 2 oxygens. There's a few things to keep in mind because you've got this extra electron density kind of conjugated throughout here. So it's kind of, there's more electron density in this range here, this pi system, which could be shielding that proton. But the other thing we have to look at is that we're looking at the NMR of a coordinated complex, right? Coordinated there. So for that matter, it's the electron density is going to be donating into the metal center. So there's a few factors at play there that you have to look at, but you'll be able to see pretty clearly from the integration of the signals which one's which, and based on that, you'll definitely be able to justify it in regards to the electron density and the shielding. But that's certainly a very good starting point, that because it's between 2 electronegative oxygens, it might be de-shielding this proton and have a higher shift. So you're definitely on the right track there. Okay, so with this deprotonated ACAC ligand, right, we're going to form a complex, and it's going to be a bidentate ligand mode. So as we've seen in the tutorials, the first arm of a bidentate ligand coordinates and makes the energy barrier for the second arm to coordinate very, very low. So you're very likely to get a strong complexation. For this complex, we're going to end up with a 3:1 ligand to metal ratio. And important to know in any octahedral complex, so that is with a coordination number of 6, you've got the chance of optical isomers, delta and lambda, which is it's hard to represent in this kind of 2D drawing, but it's basically how the bidentate ligands are coordinating, whether they're kind of going into the page or out of the page when you rotate the complex clockwise. We've also given you some information again on this complex. So we can see now this time at room temperature, it's a solid. You can see the melting point's very, very high. So at 25 degrees, it's definitely going to be a solid still. You've got the molecular mass here to help work out your theoretical yield. And importantly, take note of the solubility in water. That'll help you explain some of the observations that you see in the experimental demonstration video. So you got that there as well to look at. So we'll keep going. Okay, so we're going to have a quick look at some spectroscopy, because in this prac you do IR and NMR spectroscopy. And previously in the cobalt prac, you've done UV-vis absorption spectroscopy. So we're just going to do a little bit of background now on the spectroscopy in general and in its different forms and what we're actually measuring, because I think it's important to have an understanding of what you're actually measuring, not just look at an output and assign peaks. So spectroscopy, generally, we're measuring the interaction of energy and matter, and we're presenting that in the form of a spectrum for interpretation. So I've got here a little layout of various energy levels, right? And the classification of energy that they represent. So all the way from gamma rays through to radio. And you can see that the different energy levels have different wavelengths associated with them. And we use these different wavelengths to probe materials in different ways. So the first thing we'll look at is UV visible, which we did in the cobalt prac, or you guys looked at in the cobalt prac. Now, UV visible, we're basically we're looking at what energy level, so at what wavelength, light is absorbed by a material. And when we expose our analyte to light energy in the UV visible region, what we're actually doing, if you see in the top left here, we've got our representation of a little atom with its positively charged nucleus and negatively charged electrons spinning around in various orbital levels. And what we're doing when we expose or we hit that analyte molecule or atom with energy in the UV visible region is we're actually promoting one of the electrons to a higher energy level. So it absorbs energy and is promoted to a higher orbital. And we're actually measuring how much energy it takes and at what wavelength that energy is to promote that electron. And by doing that, we can we can find out a number of electronic properties, but at a very basic level, empirically, we can compare spectrum and we can elucidate the structure based on comparing the spectrum from one to another. So you'll end up getting materials with like a characteristic absorption. And so when you see that absorption band in an unknown sample, you can say, well, most likely I've got this material in there. That's at a basic level. As a kind of more advanced than that, you can also find a lot of electronic properties based on the absorption frequency. I'll just look at Robin's question here in the chat. For proton NMR, how do we find integration values for each peak when there's no, does practical did not have values on the peak? Okay, yeah, unfortunately, there's not a way. So the integration value, as you've said, there is, or maybe you haven't said there, the integration value is the area under a peak. So I'm sure that most of you are familiar. So if we have a peak in a spectrum, the integration value is actually how much area is incorporated under the peak. So if that's not calculated in the analysis software and presented underneath the spectrum, if that's not there, it's very difficult to measure. If you had a high resolution printout, you could mathematically measure how much area is under the peak. But if it's not done in the analysis software, it's going to be very difficult. But what you can do is, in kind of by eye, roughly, you can say that if you compare the two peaks. And I'm sure that for this Prac, I've seen the NMR, I'm sure that for this Prac, it's pretty obvious which one has a high integration value. So you can kind of qualitatively, not quantitatively, qualitatively compare the two peaks and say this one might be 3 times or approximately 3 times larger than this one. So I hope that answers your question. You can't really work it out if it's not done in the analysis software. But you probably can give a qualitative comment on which peak has a higher integration. Hopefully that answers your question, Robin. So back to the UV-Vis, yeah. So we're measuring absorption, and that's a representation of promoting an electron to a higher orbital. So that's based on the fact that electrons exist at certain energy levels based on the structure of the molecule, and they absorb energy corresponding to the gap in energy levels, and that's what we're measuring with UV-Vis. Conversely, when the electron relaxes back down to its ground state, oftentimes it will emit either in the form of fluorescence or phosphorescence, and we can also measure that as well with fluorescence spectroscopy. That's a kind of complementary technique to UV visible. So we'll move on to infrared IR spectroscopy. So we're using a little bit lower energy wavelengths here. And what we're doing with IR is we're measuring the bonds, the energy, the absorption energy of bonds between atoms, right? So UV-Vis, we were measuring the absorption energy of electrons within atoms. Here we're measuring the absorption energy of bonds between atoms. So if we start with our little very simple demonstration here using helium. So we've got our positively charged nucleus and our little electrons spinning happily around the outside in their 1s orbital. And then we bring in another helium atom, and we make it diatomic helium, right? So we've got now 2 helium atoms with electrons spinning around, and they form diatomic helium by an overlap of their orbitals, their 1s orbitals. So now you've got these electrons spinning around in these combined 1s orbitals to make diatomic helium. Now, the thing is, the positively charged nuclei, because of the orbitals of the electrons overlapping either constructively or destructively at any one time, the positively charged nuclei actually oscillate towards and away from each other as the electrons rotate around the orbitals. So from this, we can say that the bonds between the atoms are not rigid. So even though we oftentimes represent bonds as solid lines when we draw molecules, those solid lines actually represent an oscillating bond that's changing constantly. So with IR spectroscopy, we actually, we're measuring the energy of this oscillation between the two atoms. So the bond between these two, or the bond between any atoms, oscillates at a certain frequency. And that frequency depends on what atoms we're talking about and also the environment that it's in, right? But certain atoms in certain environments will have characteristic frequencies that the bonds oscillate at. And those bonds will then absorb energy corresponding to the frequency of oscillation. So like we said with UV vis, that we can measure the energy of the change in electronic level. With IR, we can measure the prevalence of certain bonds in a sample. So when you look at an IR spectrum, that's what you're seeing. You're seeing within the sample, you're seeing how much energy is absorbed at certain frequencies, and those frequencies correspond to oscillations between atoms. Hopefully that gives you a bit of background into what you're actually looking at when you see an IR spectrum, because it sometimes looks a bit messy and you just kind of pick out certain peaks and have a guess, have a stab at what they are. But that's what you're actually looking at. You're looking at the relative absorption of frequencies corresponding to oscillations between bonds. So finally, with NMR, which we're also looking at in this project. So NMR, again, we've got our positively charged nucleus. And in this case, we're going to be considering the fact that the nucleus is rotating like the Earth does. The Earth is spinning once per day. Nucleus is spinning a lot faster than that, but it's rotating like the Earth does. And just like the Earth, it's got an axis of rotation, right? And as the nucleus rotates, the axis of rotation oscillates, it moves. Now, if we put the spinning nuclei in a strong magnetic field, like we do in an NMR experiment, we expose them to a very strong magnetic field, all of the axes of rotation align. They can either be parallel or anti-parallel. So they're either pointing in the same direction or opposite directions, but they're always kind of parallel. They're always aligned to each other. Now, the axis of rotation that we can see here, this purple arrow, oscillates at a certain frequency, and that depends on the chemical environment that it finds itself in. And you can think about that looking at the Earth as well. So we've got this little GIF here. So as a lot of you probably know, the axis of rotation of the Earth is tilted by, someone told me the exact number in the last practical. I think it was 23 degrees off center. It's tilted, and it also kind of wobbles. So as the Earth rotates, the axis of rotation also rotates, and it traces out these lines in the sky. And that phenomenon is called precession. We can say the axis of rotation precesses. And the same thing happens to the axis of rotation of a nucleus, right? So if we look back over on the right, our axis of rotation of our nucleus is kind of oscillating backwards and forwards. And it would be tracing out a circle in space as well. So that that axis of rotation is oscillating backwards and forwards. And when we hit our sample with a bit of energy in the radio frequency range, what we actually do is we knock that axis of rotation with a pulse of energy, we knock it off its z-axis. So it's normally kind of oscillating back and forth close to the z-axis. And then we hit it with a pulse of energy and we knock it kind of away from the z-axis and more down towards the xy axis. So now it's oscillating like this, kind of close to the xy axis. Now that's from a pulse of radio energy, and as that pulse, and when we switch that pulse off, eventually the axis of rotation will return back to its original oscillation. And what we're measuring NMR is in NMR is we're measuring the change as a nucleus returns to its normal oscillation. So when we go from this oscillation, which is a result of the radio wave, back to this oscillation, the change in magnetic field actually induces a current in a very sensitive detector in the NMR. And that change in current, or the change in induced current, is what we're measuring in NMR and what we present in the spectrum. So again, hopefully that gives you some background into what we're actually looking at an NMR spectrum. And that's why when we talk about shielding and de-shielding, if you imagine you have a whole cloud of electrons around that nucleus that we just looked at, those electrons are going to shield the nucleus from that radio pulse that we try to hit it with. So we won't knock the axis over as much. So that's what we talk about, shielding and de-shielding. Cameron, it takes a long time for it to have a one full revolution. Yeah, I think that precession of the Earth, if we go back to this little GIF, so the circles that it traces out in the sky, I think it's either 7 years or 26 years or something, but it's a long time. It's a lot longer than obviously the rotation of the Earth or even the rotation of the Earth around the Sun. But yeah, it takes a long time. Certainly a lot longer than our nuclei. So that's NMR. So hopefully that gives you a bit of background on those three spectroscopic techniques and what we're actually measuring when we perform them and what you're actually looking at when you see a spectrum. So like we said with IR, okay, we're measuring, so this is back to IR, we're measuring the oscillation of bonds between atoms. So here we have an example of a few different oscillations that we can measure, classed as symmetric or anti-symmetric. And you can see that they take, oh, Cameron? Wow, okay, 25,000 years, 25,000 years, a long time. So I'm not sure how long it takes for a nucleus, but apparently a lot longer than it takes for it to rotate. So relatively slow compared to nuclear spin. So yeah, in here we can see various modes of vibration that we measure in IR. Can be linear stretching, which you can see in the radial row at the top, which is just away and towards the central atom. But it can also be like scissoring, rocking motions, and also kind of wagging back and forth perpendicular to the bond axis. So all of these bonds will have an oscillation that absorbs energy of a certain frequency, depending on kind of what atom is what. For example, let me just stop that there. Let me see if I can do this. There we go. For example, if we said that this central atom here was a carbon, this was an oxygen, that was an oxygen, and say we had this was protonated, and this was a double bond, right? So we see here a carboxylic acid group. We could say that this bond here, we know carboxylic acids, for example, we know that carboxylic acids will absorb, and I don't know if this number is 100% right, but around about 1650 centimeters, right? Inverse centimeters. That unit there, inverse centimeters, is a wave number. It's a measure of energy, right? Not wavelength. It's not a distance. It's not a length. It's a measure of energy. So we could say that we know from experiments that carboxylic acid carbonyl double bonds absorb at this wavelength. So then when we look at our spectrum, if we have, usually pretty messy, but if we have a peak around about 1650, in our spectrum. What we're saying is our material that we're analyzing absorbs strongly in this energy region. And based on that, we can say, well, that signal there is probably looking at this bond here between the carbon and the oxygen. And it's probably looking at, specifically, it's looking at this stretching motion of that bond. So that's what we're actually looking at in an IR spectrum, and that's how we interpret it. So hopefully that helps you guys. So when it comes to actually practical application of this theory, hopefully this helps you out a little bit with this Prac. You'll be supplied with, or you might look it up or whatever. Oftentimes it'll be a table of values and their kind of typical bonds that they represent. Or in this case, I've shown here a little kind of spectrum table of different bonds and different values. So you could look at, for example, a CO double bond. Here, based on this graphic, it exists somewhere in this like 1500 to 1800 range. And then you can look at your complex that you're analyzing and say, well, I should have a double bond here between a carbon and oxygen. So let me look at my spectrum and let me see if I've got a signal somewhere in this 1800 to 1500 range, which could represent my double bond carbon oxygen. Also, another thing to look at would be this one here. We know that in our free unbound ligand, sorry for my messy drawing. So remember, it was existing in equilibrium. In our free unbound ligand, we have this OH group here. So if that's present in our sample, we should be getting a signal in this range here. So that's a good way to have a look at the spectrum of your sample and say, do I have any unbound ligand present? Do I see any IR absorption in this range? Or has all of my ligand become bound to the complex and I only see this carbonyl bond? So that's a pretty kind of simple thing that you can get from the IR spectrum without having to interpret too many signals. So hopefully that helps you with the results sheet. As far as NMR goes, we've been through NMR a few times in various practicals. So I'll skip over it here now, and we can come back to it if anyone's got any questions at the end of this presentation. We can come back and talk about either interpreting multiplicity, or we've got some examples here that we've touched on in the tutorials, but we can go back over them again. So hopefully everyone's pretty good with a proton NMR. As far as carbon NMR goes, there's quite a bit less to interpret. There's no integration values, there's no multiplicity. So you're basically just looking at the signals that you've got. If I draw a very kind of messy carbon NMR spectrum, looking at the value of the shift and deciding what it possibly represents using a like either a table or kind of a layout like this, which tells you the typical environments that correspond to a range of shifts. So a little bit less to interpret with the 13C NMR, but very important for structural elucidation. But if anyone has any questions on that, you guys can ask me. Feel free to ask me. T has a question in the chat. Where's IR and NMR spectrum? So on views in the folder that has the lab demonstration video, they'll also have the files there for the proton and carbon NMR and also the IR. If I just, I think I've got it up here. hopefully you guys can see that window. So yeah, in this folder for lab 3.1, 3.2, you've got the demonstration video, and then you've got IR and NMR PDFs here. You also have some spectra of the Nugel or paraffin, which is the kind of, what would I say? It's like the substrate that we use sometimes for IR. So it's basically saying if you see these signals in the IR, you can ignore them because they come from the substrate, not from the compound itself. Okay, so hopefully that helps. Yeah, so that's the carbon NMR. Okay, so we'll just go through quickly here the kind of stuff that you're going to need in your lab book for this practical. So I've taken the method directly from the lab manual. And the first thing to do when you're looking at the method and trying to compose your SDS or your hazard section is go through and look at what materials you're using. So here we've got the reagents, aluminium nitrate monohydrate with the empirical formula there. So the 9, in case you're not familiar, the 9 waters are like co-crystallized solvents, and that comes from the nonahydrate, which means 9. So it's got 9 waters for each aluminium nitrate molecule. So that's important when you're working out your molecular weight, to take into account the fact that it's got 9 waters for each 1 aluminium nitrate molecule. What else do we have? The acetylacetone, and we've got the empirical formula here. Important to note that it's protonated, right? So we've got all 8 protons, hasn't been deprotonated yet because it's just in neutral conditions. So when you're working out the theoretical yield, etc., use the protonated form. What else do we have? We've got the ammonia, 2 molar ammonia. So that is a reagent, but it's more of a spectator reagent. So you don't have to consider the stoichiometric ratio. We've got water as a solvent, chloroform as a solvent, and we've got this aluminium hydroxide, which is a expected or unexpected byproduct, and the formula there. So identifying all of that, they're all things that you should put in your SDS for this prac. You can leave out water, it's innocuous, but the rest of it put in your SDS, in your hazard section for the prac. And part of this prac is working out the molecular weight, number of moles and stoichiometry to give you a limiting reagent and theoretical yield. So we're going to go through that very quickly now. As far as stoichiometric ratios and limiting reagents goes. It's a concept that I've been asked about a few times over the years teaching on campus. So we'll go through it now just so that everyone understands. And the way we're going to look at it is we're going to take a quick trip to the molecular bicycle factory, which is a strange analogy, but bear with me. Hopefully it makes sense to some of you. So at the molecular bicycle factory, they make bikes, obviously. And each bicycle needs a frame, 1 frame, and 2 wheels. So you can probably see where I'm going with this. We've got a ratio here. And I have a lot of fun with this analogy, so just amuse me. So in the factory, we've got frames and we've got wheels at a ratio of 1 frame to 2 wheels to make a bicycle. And in the factory, we make the frames, we make the wheels, and we build up a little stockpile. So here we've built up a little stock of 3 frames, and we've also built up a little stock of wheels. So we've got 1, 2, 3, 4, 5 wheels. Now that we've got a few frames and a few wheels on the shelf, we start putting together our bicycles. So we start assembling them, and we produce some very fine-looking 2-wheelers. And we get to a point where we can't make any more bicycles because even though we've got a frame, we don't have enough wheels. We've got a frame missing a wheel. So we'd say in this case, the wheels are our limiting factor. We could make another bicycle. We've got enough frames, but the wheels are holding us back. again, you can see where I'm going with this. We're going to take it from the molecular bicycle factory to something a little bit more relevant to us, that aluminium ACAC3 factory. We'll get rid of him and put our complex there. So same concept applies. We've got aluminium and ACAC as our items that we need. And in this case, the ratio is not 1 to 2, it's 1 to 3, right? As we saw, or we can see in that structure diagram, we've got 3 ligands to 1 aluminium. Cameron, you could make a unicycle. We could make a unicycle, but it's a molecular bicycle factory, not the molecular unicycle factory. We're only interested in bicycles. Similarly, we're only interested in aluminium ACAC3. We're not interested in aluminium ACAC2 or 1. We're only making one product here. So again, we've built up some stock on the shelves of our aluminium 3 plus cation, and we've also built up a stock, quite a bit of ACAC. We've been busy making ACAC, and we're ready to start assembling them, putting them together. So start pumping out our 3-to-1 ACAC to aluminium product. And again, we reach a point where we want to make more. We've got enough aluminium to do it, but unfortunately our ACAC is what's limiting us. So in this case, we say the ACAC is our limiting factor. Now, the thing is, when you get questions like this, or you're doing this in your lab book or whatever, and this is something that I do every time I do an experiment in my research, I have to consider the stoichiometric ratio, the limiting reagent, and work out my theoretical yield and everything. But of course, I don't draw a factor in. I don't draw all these little bits and pieces. I do it numerically, and you will too. But it's the same concept. You start with, and I've just made up a number here, you start with a certain number of aluminium ions based on how much of the starting reagent you've measured out. And you start with a certain number of ACAC ions based on the starting reagent that you've worked out. The ratio is 1 to 3. So if we were making aluminium ACAC3, based on the amount of aluminium we have, if we multiply that by 3, we'd require 0.0039 moles. Let me just get my drawing here. We'd require 0.0039 moles of ACAC. Now, unfortunately, we only have 0.00309 moles of aluminium ACAC. So that tells us that if we want to use all of the aluminium, we're actually limited by the ACAC, because what we require is 0.00339, but we only have 0.00309. So that's what's holding us back. That's what's limiting us. So we've identified the limiting reagent. The next thing to do is work out our theoretical yield. So the fact that we're limited by the aluminium, by the ACAC here, that's what's holding us back from making any more. We're going to have spare aluminium sitting around, unused, but we're going to use all of the ACAC. So because we're using all of the ACAC, this is the number we use to work out our theoretical yield. So we're saying that once we've finished assembling all our aluminium ACAC, we're going to have used 0.00309 moles of ACAC. We used all of it, all the ACAC. But we want to know how many aluminium ACAC3s we've made. Well, based on the ratio, we'd have to divide that by 3. We've used all the ACAC, and we've divided by 3 to find out how many complex molecules we've made. So dividing that by 3, we get 0.00103 moles. So that's our theoretical yield in moles. Now we multiply that by the molecular weight of the product, and that gives us our theoretical yield in grams. So hopefully that is a little bit clear to you guys. I'm not sure if it's something that you struggle with or anyone struggles with, but it's certainly something I get asked fairly regularly teaching this unit. So hopefully that gives you a better understanding of how to work out the limiting reagent based on the stoichiometric ratio, and then based on the limiting reagent, how to work out your theoretical yield. And you'll need to do that. You'll need to do that for this Prac. T, would you please go through the equation? I tried to write not balance. I did not know what substance I missed out. Okay, yes, we can do that. Thanks, Cameron. I'm glad it resonated with someone. Okay, let me just pull up something that might help us. Not that. Okay. Get back to this. All right, so we can clear this. We're done with that. As far as the equation goes, what's the best way to do this? Okay. So what are our reagents? Maybe I should go back to the method section. Yeah. Okay, so we've got starting material aluminium, starting material ACAC, and then we've got our ammonia as a reagent as well. So what we can do is we'll write it out here. Apologies, I'm not going to use subscript because it's going to take me too long. So just imagine that all the numbers are subscript. So we've got our two starting materials, aluminium plus the ACAC. And then we've got our ammonia as well. Okay, I'll put it in brackets to make it a bit more clear. Okay, so our final product, maybe we should write that as well, so we know where we're going to end up. So our final product is going to be so aluminium C5H8O2, and three of them, right? So the C5H8O2 is just ACAC. In fact, that's going to be 7 because it's deprotonated. And so yeah, the C5H7 or H8, depending on whether it's deprotonated, O2 is our ACAC ligand. So the product is aluminium ACAC 3. Plus, we're going to have some byproducts, no doubt. Okay, and then we'll put a little arrow in here. So when we're working this out, the first thing that we can look at is how many ACACs we're going to need. So in our final product, we've got 3 ACACs to 1 aluminium. So if we're starting with 1 aluminium nitrate monohydrate, we're definitely going to need, I wish I could edit that. Anyway, we're going to need 3 of the ACACs. Does that make sense so far, T? So we'll need 3 of the ACACs to every 1 aluminium. Then our NH2 is deprotonating the ACACs. Isabel, yeah, sorry, as per usual, if you guys just want to at some stage put your name and student number in the chat, and then I'll, after we finish up, I'll record all the attendance. So yeah, if you do have to shoot off, it's been the hour, so if you do have to shoot off, just put your name and student number in the chat so I can record it later. And this will be recorded and uploaded, so you can watch the rest of it later. No worries. Yeah, so to get the final compound, we need 3 of the ACACs for every 1 aluminium. The NH2 is deprotonating our, sorry, NH3 it should be. Should be NH3. NH3 is deprotonating our ACAC, and we've got 3 to deprotonate, so we're going to need 3 of the NH3. We need 3 of them because you're going to deprotonate 3 ACACs. So that will give us our final product, and then we got to look at the byproducts, and the byproducts that we end up with is the ammonium that's picked up a proton, and we're going to need counter ions to the ammonium, and they're nitrate from the aluminium. So the aluminium nitrate becomes the counter ion to the protonated ammonia. And then the other byproduct that we have, of course, is going to be our water from our starting material. So nine waters as well. So that'll be our byproducts. Does that answer your question, Tian? Does it make sense to everyone how we come up with that formula? Hopefully, yeah, Cameron. Okay, cool. Okay, all good. So we'll finish up pretty quickly because it's 1:10. No doubt people have places to be. So we've been through limiting reagents. The last thing I'll say is that with the procedure that you have to write in your lab books, what we're looking for there is that you have re-presented the procedure in a way that shows you've understood, you know what we need to do, you know what needs to be done in the experiment, and you've understood why it's being done. So the way I do it in my lab book, the way I did it in undergrad, the way that I do it in my research is by drawing what I'm doing. You guys can do it in any number of ways. You can do flowcharts, you can do whatever, but as long as it shows that you've thought about it, you've read it, you've thought about it, and you understand why we're doing things. So I'll go through very quickly. So this is the way I would do it, writing down the chemical species for each step, representing the fact that we're stirring, we're adding dropwise, a cooling step, filtration step. So in this case, in your lab books, we'd be looking for an explanation as to like why we do a step like this. You know, so why do we cool on ice? What's the purpose there? Also in these steps where you're filtering, important to say like what you expect, what species you expect in the filtrate, what species you expect in the residue. Explain kind of why we're filtering it and what we're filtering out. Dry it out. I mean, drying it's pretty obvious why we do it. Another filtration step where you can comment on what you'd expect to be in the residue and what you expect to be in the filtrate, and then an evaporation step to finish it off. So that's just one way to represent the procedure. It's up to you guys how you do it, but as long as you're showing us that you've read it, you've understood it, and you kind of account for the chemical species, so you understand the chemistry of it, And you also explain why we do certain steps, so you understand kind of the experimental side of it. So hopefully that gives you, you don't have to do it that way. Like I said, there's many different ways to do it, but it's one way to do it. So it's 1:10, so we've already definitely done the hour and a little bit, but if anyone has any questions, now's the time to ask for sure. Any questions about this prac that we've talked about today, or any of the spectroscopy stuff, NMR, etc. Just let me know, put it in the chat, or feel free to turn your microphone on. Hopefully all of that made sense to everyone. So can you show how to calculate integral in results sheet? The results sheet for this prac, is that what you're asking? Yeah, okay. So like we spoke about before, you won't be able to calculate mathematically a integration value just looking at the spectrum, because unless you have a very high resolution spectrum, you won't be able to zoom in and measure the area under the curve. So you can't calculate the integration value, but what you can do is calculate the integration number, right? Which is a ratio. So if we look at some of these examples here, remember that integration is just a ratio of the relative abundance of protons in a certain environment. So if we look at this example here on the left, we've got one set of protons in a chemical environment here, and we've got another proton in a very different chemical environment. And if we didn't have these numbers, we didn't have the integration values, just looking at the protons, we could say, well, there's 3 times as many protons in this environment compared to this one. So I've got a ratio of 3 to 1. So if we were asked for the integration values for this spectrum, we could say that considering this proton is this signal here, and these protons is this signal here, we could say the ratio is the integration value, or sorry, integration number ratio is 1 to 3. So we can do the same for this spectrum here. Here we don't have any integration values. They haven't been provided for us. There's nothing here. But what we can say now that we've assigned, so we've got these orange ones here, red ones here. So we've already decided which signal belongs to which protons, okay? And we can say, all right, these protons here, there's 3 of them. These protons here, there's 2 of them. And these protons here, there's 3 of them. So our integration numbers would be 2, ratio of 2. Maybe I'll do it underneath. 2 to 3 to 3. That'd be integration ratio. Does that make sense? Does that answer your question? So like in this spectrum here, I can't actually go in and measure how much area is under the curve of these little curves. I've got no way of doing that. But what I can do is I can look at the structure and I can say, well, I know for sure that the ratio of areas under this curve, under that curve, and under that curve is going to be this ratio. Okay, great. You got it. That's an important thing to remember, that integration is just a ratio. That's all it is. Okay, any other questions about anything else? Doesn't seem like it. Okay, if that's all, guys, we'll leave it there. And like I said, this recording will be up on Views, so you can go back and look at it later. Remember that the preliminary results sheets are due on the 21st. Please attempt them. as best as you can before asking us any questions via email. But if you have attempted them, we'll be happy to help with understanding. So I think that's it. I'll catch you guys next time. Have a good afternoon. Thanks, Kyle. Thanks, Shane.